In this lesson, we're going to look at an introduction to linear systems. So what is a linear system? A linear system is just two or more linear relations. And recall that linear relations are just a relationship between two variables, x and y, and it results in a straight line graph because we have a constant rate of change between those two variables. So what we need to do is take a look at some things that we learned in our first unit on linear relations to help us out. So we want to make sure that we are able to graph a linear relation from the slope y-intercept form. So our slope is the m, that's the number that comes in front of x, and the y-intercept is the other number that is not being multiplied by x. So let's take a look at a couple of examples. Y equals x minus 1. So the number in front of x, there is no number. What number do we multiply by x that doesn't change it? That would be 1. So our slope here is 1, and our y-intercept is the other number that is not being multiplied by x. So that is a negative 1 here. In the next question, y equals negative 4x plus 1. Negative 4 is the number in front of x, so negative 4 is our slope, and the other number not being multiplied by x is a positive 1 or just 1, so that is our y-intercept. We also want to make sure that we can graph using our slope and y-intercept, so recall that our y-intercept is a specific point which is on the y-axis. So whatever this number is, we find that number on the y-axis. And our slope is our rate of change. So our slope is a rise over a run, which means we need a fraction, we need a numerator and a denominator. When we have a whole number, we only have our numerator, so we need a denominator. What would we divide by that doesn't change it? And that is always 1. So both of these are whole numbers, which means our run for both of them is 1. So let's quickly graph these. We have for the first one a y-intercept of negative 1, so I'm going to go down the y-axis until I find negative 1, and then I'll use my slope, which is up 1 to the right 1. And that pattern continues. So our slope is our rate of change. That's something that continues on and on and on. And it can move in the opposite direction as well, so down 1 and to the left 1. So same pattern here. And once we have multiple points, we can then draw in our line. So this is the line for y equals x minus 1, so that's the yellow line. And then the next one, we have y equals negative 4x plus 1. So my y-intercept is positive 1 this time, and my slope is negative 4. So down 4 and to the right 1, down 4 and to the right 1, down 4 and to the right 1, or in the opposite direction, up 4 and left 1. So once we have enough points in there, we will put in our line for that one as well. And there we go. So this is the skill that we want to transfer from our first unit of linear relations, understanding y equals mx plus b. M is the number in front of x, and that is our slope, our rate of change or pattern that we use to get more points. And our starting point for graphing is our y-intercept, so the number that is not being multiplied by x. So we're going to start by plotting that and then use our rate of change to find more numbers. So in this unit, we are going to be doing something called solving a linear system. So what does that mean? Solving a linear system just means that we are going to find what is called the point of intersection. So that is the point where the two lines cross. But can we only have one point of intersection? So let's take a look at a few questions here and see what we find. So we'll practice our skill. The number in front of x is our slope, so we have a 2 for this one, 1/2 for this one. So 2 and 1/2 are the slopes we have. And the number that is not being multiplied by x is our y-intercept. In this case, I have no number. So what can I add that is nothing? And that would be 0. So my y-intercept here is 0, and here it's -2. And let's just do these for all of them. So here I have 1/2 for both slopes. And here I have a +3 and then a -2 for my y-intercepts. Over here we have 2 and 4 for our slope and our y-intercept. And the next one is not in y equals mx plus b or slope y-intercept form. So we want to figure out some points we can plot. So one of the things we often do here in this case is that we set our y to 0. So 3 times 0 minus 6x equals 12. Anything times 0 is 0. So I have -6x is 12. I'll divide by -6. And I'm left with x equals -2. So I have a point there. X is -2, and that happens when y is 0. And then the next thing I can do is substitute in a 0 for x and solve for y. So that makes this one 0, so 3y is 12. I'll divide both sides by 3 to get y equals 4. So in this case, when x was 0, y was 4. So those are 2 points that I'm going to plot. I'll just write them here so they're close and I can see them when I get to this question. So there we go. We have our slope and our y-intercept for all of these. Now let's take a look and plot them and see if we can find a point of intersection. So my starting point is to plot my y-intercept, the first one, b equals 0, and then I'll use my slope, which is 2, which means 2 over 1 if I don't have a run. So up 2, right 1, and then down to left 1. And then we'll draw in our line, and we'll see. So there is that linear relation. And then we'll plot the next one. So b, or y-intercept, is -2. So on my y-axis, I'm finding -2. And then I'm using my slope of 1 over 2. So up 1 to the right 2, up 1 to the right 2, continuing on, and down 1 and to the left 2, continuing that pattern on the other side. Then we will draw in our line. So we can see here that we have one point of intersection happening. So we have one place where our 2 lines are going to cross. So when we take a look at these, what we notice is that our slopes are different, and so are the y-intercepts. So both of these are different, slopes and our y-intercepts. And at this point, we're seeing one point of intersection. So let's see what happens with this next example. So my first question, I have a y-intercept of +3, and then a slope of 1 over 2. So up 1 over 2, that continues. And then in the opposite direction, we'll draw in our line. So every single point on this line, not just the ones that I plotted, but one of the reasons that we add in this line is that every single point on this line is a point. So we actually have not the number of points I plotted, but there are an infinite number of points. We're simply plotting nice whole number points that we can read easily off of our graph. And then we also have arrows on both ends of the line because this line extends forever. So we have any single point that we take, so I could take 3.2 6, 8, 9, numbers could go on forever. I could plug that into my equation, and that would spit out my y value, and it would also not be a whole number. So there are an infinite number of points along this line, and that's why we draw that line in. We're simply using some nice points to plot so that we can figure out where that line goes. Okay, next one. B is -2, so along my y-axis I find -2, and I'm using, once again, up 1 over 2 as my rate of change, going on in the opposite direction as well, down 1, left 2. And once I have enough points, I'll draw in my line. Now, on this graph, these two lines run parallel to one another. So they're running in the exact same direction. They have the exact same rate of change. They're going to continue on forever in both of them, going up 1 over 2, up 1 over 2, down 1, left 2, down 1, left 2, which means they're never going to cross. So we can see here that there's the same amount of space all the way along. So what we see if we compare is our slopes are the same, but our y-intercepts are different. So when our rate of change or our slope is the same, but we have a different initial value, here we don't have a point of intersection. So let's see what happens in this last case. So I have first a y-intercept of 4, and then a slope of 2, which is 2 over 1, so up 2, right 1, or down 2, left 1. And then we'll draw in our line. And our next one, we have, so our y-intercept happens when x is 0. So that means that my y-intercept is 4. So that's the same number that I have here. So I'm just going to circle it in orange. So that is also the same. And then -2 and 0, which is over here, which is also the exact same point as the other graph. Now, if I look here, I'm going up 4 and over 2. So that's my rate of change over here. So I have 4 over 2, and 4 divided by 2 is equal to 2. So I have the exact same rate of change here, up 2 over 1, up 2 over 1, up 2 over 1. So what we can see is all of our points are actually the exact same. So as I draw in my line, my line goes exactly on top of the other line, which means every single point that is on one line is on the other line. So in this case, what I see is that every single point is a solution, and if I have an infinite number of points on each line, then that means I have an infinite number of solutions. Now as I compare here, these two numbers are the same, and so are those two. So let's summarize these findings. So when both are different, I have one solution. When slopes are the same, but y-intercepts are different, I have no solutions. They're running parallel to one another. And when both slopes and y-intercepts are the same, I have an infinite number of solutions. So let's record those results here in one place. So if slopes are different, this is where we have one solution or one point of intersection. When slopes are the same, but we have different y-intercepts, this was where we had no points of intersection because they run parallel to one another. And when slopes were the same, but and so are y-intercepts, this is where we have an infinite number of solutions or infinite number of points of intersection because every single point is the same for both. So let's practice a few questions here. What we want to do is from each equation, we want to figure out our slope and y-intercept and then predict, will we have one point of intersection, one solution, no solutions, or an infinite number of solutions? And then we'll plot to double check. So here I need to rearrange. I need a y equals, which means I need to move my negative 2x and my positive 4 over. So the opposite of subtracting 2x is to add it, and the opposite of adding 4 is to subtract it. So we'll move those to the other side. I'm starting with 0 on the other side, so I'm going to have 0 plus 2x, or just 2x, and then I'm subtracting my 4 to move it over. So I have a slope of 2 here, of negative 1 over 3 here, and a y-intercept of negative 4 and positive 3. And anytime I don't have a run, when I have a whole number, it's 1. And then negative 4 and positive 3. So from here, both slopes and y-intercepts are different. So what happens at that point? We have one point of intersection. So this is what we are predicting. Since M and B are different, we predict that there is going to be one solution or one point of intersection. So we can quickly graph those to double check. In the video, I'll just graph this one question and we'll do the predictions for the other, and you can graph those yourself to check. So we have negative 4 and then 2 over 1. So negative 4 as our y-intercept, and up to over 1. And we're down to and to the left one, moving in the opposite direction. And then our next one is a y-intercept of positive 3 and a rate of change of negative 1 over 3. So down 1 and to the right 3, and that continues. And I can see that one point that I drew on was exactly on top of a point that was in the other one. So that's going to be my point of intersection, but I'll draw in my lines to see this. So I have one linear relation here. So that yellow one was y equals 2x minus 4. And then the orange one will be the y equals negative 1/3 x plus 3. Whoops. There we go. Okay, so I can see that my prediction was correct. There is one point where these two linear relations intersect, and so there's one solution or one point of intersection. I can identify the coordinates of the point of intersection, so I can say POI, or point of intersection. So always x coordinate first and then y. So along the x, I'm at positive 3, and along the y, it's at positive 2. So this point is 3, 2 for the point of intersection. So there is one point of intersection. That was correct. And it happens at x is 3, y is 2. So with these ones, we're just going to make our prediction, and then you can graph them yourself. So my slope here, number in front of x, is 1/2, and my y-intercept is 2. In this question, I need to rearrange. So I'm going to keep the 2y on this side. X is going to move over, so subtracting an x becomes adding an x on the other side. Subtracting 4 becomes adding 4. And I need to get 1y, which means I need to divide everything by 2. So 2 divided by 2, I'm left with 1y. Now over here, the number in front of x is my slope. So I see that I have under my fraction line a 2. So that's my denominator or my run. I still need to rise the top number. So what's the one number that we can multiply by x and it doesn't change it, so we don't have to write it? And that is a 1. So my rise here is 1. So x over 2 is the same as 1/2 x. And then our y-intercept, 4 divided by 2 is 2. So my y-intercept is 2, and my slope is 1/2. So let's compare. I have the same slope and the same y-intercept. So that means these are the exact same linear relation. The lines are going to run exactly on top of one another. So I am predicting that since m and b are the same, that I have an infinite number of solutions. So the two lines will lie right on top of one another, and every single point along the line is a solution. It's a point of intersection. It's a point where one line touches the other. So you can graph those two to see. And then we have one last question here. So -2 is our slope in this one, and our y-intercept is 4. This next question will rearrange, so the y will stay. 6x is going to become -6x on the other side, and then +9. We'll divide everything by 3 so that we get to 1y. -6 divided by 3 is -2, and 9 divided by 3 is 3. So our slope is -2, and our y-intercept is +3. So here my slopes are the same. So slopes are the same, but y-intercepts are different. That means they have a different starting point, but the exact same rate of change. So they're going to run parallel to one another and never touch. So my prediction is that for this question, or this system, this linear system, there are no solutions. So once again, for these two questions, you can now plot these two linear relations for each question, and then see if our prediction of infinite solutions here and no solutions here is correct.